All right, so to start, when we talked about vectors, there was I called it a key insight to helping solve a lot of those vector questions. Right? The key insight was to realize that if you have some vector, whatever it is, it's going to have two parts that we're going to break it into, right? A horizontal and a vertical. Left and right and an up and down. A x and a y. However you thought about it, or based on what the problem says, that could be a variety of different things. But the key insight for vectors was a vector in space with some angle and some magnitude. You can break that into its pieces, right? Into the x and y or whatever. The key insight for projectile motion. It's the pen to work. You can break projectile motion, which we defined last week, right? Projectile motion, just motion in two dimensions, right? A projectile goes forward and it goes up or down, it goes, whatever. But you have two dimensions. The key insight for projectile motion is that you break those two dimensions into two separate problems. Any projectile motion problem, or at least most of them, depending on how they're written, is going to have two different components, a horizontal component and a vertical component. You saw this if you did the homework last night. All right, where you had some kind of thing, a ball was kicked, a cannonball was shot out of a cannon, a bow and arrow. The example we're going to do here in a second is a motorcycle driving off a cliff or whatever. But the key here is there is a vertical component and a horizontal component. They're going to be related, but they're going to have some different rules when we get into the actual problems for them. So let's do a problem. Let's look through our sample problem. So get out your Chromebooks. Go into the Bellwork section in Classroom, or at least one of you at each table. I don't know that everybody necessarily needs their own open. This is just so we can look at it while we fill this in our notes. You have this image that I have up on the board. You have this in your Chromebooks under Bellwork. Slide number 6 or something. So take a moment and get that opened up. Going to be in Classroom under Bellwork, Unit 2. It's in there, right? Yep, and all I want you to do on your Chromebook is pull up this image so you've got it, so you can refer to it, because we're going to be writing in your notes, and I'm going to take it off the screen here for a moment. So, looking at this problem, I want you to take a moment, look at this problem as drawn. How is this related to the lab we did with the pennies? How is this related to the lab we did with the pennies?
They have different...
What's that?
The table's like the cliff.
Table is like the cliff, yes? How can we use what we observed with the penny thing to help us just kind of piece through how this is going to work? And what I want you to imagine, this is...
They have different horizontal movement for the same vertical.
So this is probably terrible, but let's play make-believe that we don't have one stunt driver on a motorcycle, but we have two. One of them drives off the cliff horizontally, right? And the other one at the same moment just gets dropped from the edge of the cliff. Based on our penny experiment, who hits the ground first? Yeah, they both hit the ground at the same time. So I want you to remember that, because we're going to try to use that insight to help us solve this problem. And ultimately, we are trying to determine how fast we need to drive off this cliff in order to land at a certain spot. I think it says 90 meters away. So let's start by trying to find out how long it takes, what the time is for our motorcycle stunt rider to complete going from the top of the cliff to hitting the ground. And if we think about two cliff jumpers, I don't know, riders, whatever we want to call, both of them would hit the ground at the same time. The one that is just dropped straight down and the one that goes off at whatever the speed is. Correct? And we tried that with our penny experiment. That's kind of why we did that. So now let's go back to the math. We have a vertical component of our problem. And now this starts to look a lot like Unit 1. Right? Where we have velocities, accelerations, distances, times. There's a reason we did all that stuff in Unit 1. It's so that we can come back to it now, and this is old hat. We can figure this out. So let's start thinking about how we can fill these things in. What is our initial vertical velocity? Do we know this? The moment he drives off the cliff, what is your initial starting up and down velocity? Zero. Why zero? Yeah, you're at a height. You had no, until you drive off the cliff is holding you up. You're not moving up or down. But as soon as you drive off the cliff, your initial starting vertical velocity is 0 meters per second. And the question didn't give us that. It didn't say, hey, the starting vertical velocity is 0. You know that because of what we're talking about, the whole situation. Do we know the final velocity at the bottom for this poor guy? Okay, what about acceleration? Do we know that one? I heard a no and I heard a number. Do we know the acceleration in the vertical direction? What's that? Gravity. In all of these projectile motion questions, we're going to have gravity. Right? That'll be one of the things, one of the knowns that we're going to be able to plug in. I know we used 10, I think it was last week for one of those problems. We'll be using 9.8 meters per second squared going forward for the acceleration due to gravity. Just that 10 meters per second thing was kind of a one-off. What about distance? Do we know distance? Why 50? Yeah, that's how far it's going to go, right? Whatever the height of the cliff, vertically, if we're talking about going from the top of the cliff to the bottom of the cliff to, splat on the ground, we know our distance. So 50. Why did I make it negative? So again, distance is just 50 meters. That's how far we're going to go. But if we're talking about displacement, right, and actually adding direction to things, I'm going to make this negative 50 meters. What about time? Do we know the time? And what about average velocity? Do we know that? No. So now we filled out what we know. What we know intuitively, what the question gives us, what the situation is telling us. And now we can go shopping. Right? Now we go shopping down our list of equations to see what we can solve for given this information. And right now the one I'm really probably looking for is time. Right? Because ultimately I'm going to need time to know how long it takes to fall. Right? Because that's going to be the same for somebody falling straight down, somebody that's a projectile, any of the above. How can we solve for time? What equation do we have that's going to help us solve for time? Again, this is the shopping portion here, right? Where you need to look at your equations. This might not be automatic. Ooh, use this equation. We have initial velocity, we have acceleration, we have distance, and we're looking for time. Which of those equations, 1, 2, 3, 4, 5, I guess, or 6, can we use to find time? Any guesses? Any takers? Which one? Number 4. So distance, half a t squared plus b by t. How can we make this equation a little less messy? Yeah, what can we get rid of here? This whole portion is going to be what? 0. Why 0? Yeah, initial velocity is 0, so 0 times time, whatever we find for time, is going to evaluate out to a 0. So that makes that one really easy. So now all we have to do is start plugging in and finding time. Now again, there are 2 ways to do this. I don't really care which way, whatever way you're comfortable with. Some people just plug in the numbers here and solve it with algebra. Some people figure out the algebra, find the equation, and then plug it in afterward. I am the second version. So I am going to, let's just get rid of this. So I'm going to solve this equation for time. First, I'm going to get rid of the 1/2. Multiply both sides by 2. I get 2d at squared. Trying to get to time, so get rid of the acceleration. T squared equals 2d over a. And then to get rid of a square, take square root. Time equals the square root 2d over a. So now I just plug it in. So we can do that. I got a little bit of space over here. Time equals square root 2 times the distance was 50 divided by negative 9.8. Time equals, anybody got a calculator?
3.19.
So now we need to go back. We can plug that into our list of information. How does knowing the time help us with our scenario? Now again, remember your pennies. The time it takes something to just fall straight down 50 meters is the same time it takes something that's launched horizontally to also fall 50 meters. It's the same amount of time. So for our motion in the horizontal direction, I, V, F, A, D, T, V, F. Let's see what we can fill out here. Do we know the initial velocity? Look at what the question asks, and that'll help you figure that out. Do we know what the speed is, the velocity of him driving off the cliff? No, that's what it's asking us, right? Is how fast do I need to go off this cliff in order to land at some certain spot? If you read the question, that's literally what it's asking. So we don't know VI, we don't know VF. Do we know acceleration?
Yeah.
What's our acceleration in the horizontal direction? What's that? Nope, that was vertical direction. There's gravity acting in the horizontal direction. What force is acting in the horizontal direction here that would accelerate us or slow us down? Think about this. Think about the example we did with the cannon and the cannonball. What number did you keep writing over and over and over through that whole question? Flip back a page or two in your book. Did the horizontal velocity ever change? No. So if the velocity doesn't change, what's the acceleration? 0. Don't make this harder than it has to be. Right? What's the distance we're going in the horizontal direction? And again, this is from the question. If you look on your Chromebook, how far are we going? 90 meters. How much time is it going to take us to take this horizontal journey that we're talking about? Is that in the question? No, but what did we find a moment ago? Yeah, we do know the time. The time for the pennies, right? The time for the penny that dropped straight down and the time for the penny that was flung off was the same. Right? So we have the time. Time here is simply 3.19 seconds. And now the last key insight here, or the last thing to consider in this question. If our acceleration is 0, right? We're not speeding up or slowing down through the course of this horizontal problem. What do we know about these 3 quantities? What's that? Not 0. There's some horizontal velocity. But what's similar between these 3 things? They're all the same. Why?
Because if it doesn't accelerate or decelerate.
Yeah, if we're saying we have 0 acceleration, right? It's not speeding up or slowing down. Your starting velocity, your ending velocity, all the velocities at all points in between are all going to be the same. That's what zero acceleration means, right? So now we're going to go shopping again. Given that we know distance, time, and we're looking for velocity, what equation can we use? What kinematics equation can we use to solve for, in this case, we're trying to figure out one of those 3 velocities. They're all the same. Yeah, average velocity. The first equation we ever learned, average velocity equals change in distance over change in time. Now we just plug this up. Well, VAV, our distance was 90. Our time was 3.19 seconds. So how do you do the math?
28.2.
What was it?
28.2.
28.2 meters per second. And again, with 0 acceleration, can we now find what our initial velocity was? If we solve for VAV, right, 28.2, what's our initial velocity?
28.2.
This is the speed we'd have to drive off the cliff at in order to land exactly 90.0 meters later. Assuming no wind resistance, assuming you drive straight off the cliff is flat, the ground is flat. Again, we're making some assumptions here, but ultimately, this is the journey for projectile motion. This is how the math works out. And the trick with the math here, again, none of this math is difficult. We've done all this math before. Heck, it seems like we've been doing this math for months. The hard part here is not the math. The hard part here is thinking about what's happening. Well, somebody falls, somebody whatever. And again, some of your important things to remember for these problems. What's my acceleration going to be in the vertical direction? Vertical. The up and down direction. What's my acceleration always going to be? What problem or what thing do we always have vertically? Gravity. What's our horizontal acceleration going to be? That's the one that's going to be 0. Let's keep going. How do I make this? Here we go. First, just let this problem soak in. This is the next slide in your Chromebook if you want to see a version that you can read without having to look up. So now we're kicking a football. Kicking it at some angle, some initial velocity. We're asking questions about maximum height, time of travel, total distance, velocity vector, acceleration vector. To get started here, I want you to think about our key concept from all the velocity problems. What's the first thing you're going to have to do here? After you draw the picture and you read the question, what's going to be your first step? The first thing that you're going to have to evaluate, the first part of this problem. The first thing you would do to proceed. This looks terrible, Clymer. This question has like 8 parts and it's a paragraph. Find the different parts. What do you mean find the different parts? I agree 100%. What do we need to do first? What parts are we looking for here? What's that? Yeah, so it gives us this first green arrow, right? But what should we do? This gives us our angled green arrow. This is the actual kick, launched off at some angle with some initial velocity. Is that going to be helpful for solving a projectile motion problem? A problem in 2 dimensions. Is a single dimension, a single direction going to help us? No. What do we have to break this into? Horizontal and vertical. To do that, I'm going to expand this out. We have some angle here, 37 degrees, and the magnitude is 20.0 meters per second. So if I'm starting with this vector, this velocity vector, what should I do next? Find both sides. How are we going to do that? SOHCAHTOA. It's just trig. Again, here we go. The math here is not hard. We have a hypotenuse, right? We have our angle measurement. We can quickly and easily break this into our x and our y components. For practice, go ahead and do that in your notebooks under where you're starting this problem. And again, this is like a T-chart. When you're going to do some conversion, step 1 is draw the T-chart, write down what you know, copy the units. You can do a lot of a T-chart without even thinking about it. Right? Without even getting started, I know what I need to start with. Draw the T-chart, put in what I'm given, copy my units down. The rest of it you got to figure out. But I know I can do the first steps. Well, in a projectile motion problem, if you're given some angle and some magnitude of a vector, step 1 is going to be break this into its horizontal and vertical pieces. And in general, that's going to be SOHCAHTOA. figs. Okay, so now it's just Sokotoa, right? Good. All right, we're punching numbers into the calculators. All right, so what next? So we've done the easy part. The easy part is the Sokotoa, break it down into pieces. Let's go back to the question. What is this asking us? We're looking for the maximum height.
Vy equals 0.
Let's go back here. So for our problem, we're going to have a vertical, horizontal. So the first part of this problem asks us simply, how high up does our ball go? So if we're talking about height, which of our dimensions do we care about here, vertical or horizontal? Vertical, right? We're trying to see how high up this ball goes. Right? So which velocity is going to be important to us?
Vertical.
Vertical. A, D, T, B, N. Here we go. Let's start figuring these things out. So, based on our Sokotoa, what is our initial velocity in the y direction?
12.
Why 12?
This is the vertical one.
Yeah, that's the vertical piece of the triangle we just solved, right? So we start at 12. Do we know our final velocity? Think about what we're asking. Right? At the peak, at the highest point, you're thinking in the right direction, but not velocity. You're thinking of acceleration.
0.
Why 0?
Peak.
Yeah, so think about when you throw something up, right? A projectile. At that peak, right before it changes direction and comes back down, for that split second, the velocity is what? 0. But Climber, in the last problem, we didn't know the final velocity. You're right, because we didn't care. We didn't need to know it. Right? But now we want to know the final velocity. We need that piece of information for what we're solving. And that's part of the challenge of these projectile motion problems. They're not all going to be a motorcycle driving off a cliff. They won't be samey like that. They're going to be different. In this case, we're looking for vertical height. What's our acceleration vertically? What is acceleration always in the vertical direction? 9.8. That is our acceleration. That's gravity. Again, all of these problems are different, but they all have some similar pieces. And in this case, one of the most similar pieces is always going to be acceleration in the vertical direction is gravity. What about distance? Do we know distance? No, that's what we're solving for. What about time? Does it tell us the time? No. What about average velocity? Do we know that? Doesn't say that anywhere in the problem, but what do we need to know to figure out average velocity? VF and VI. So can we find average velocity? Yeah, that's pretty easy. What is it? So now we need to go shopping. Shopping is fun. Love me some shopping, especially when, you know, you have money. Shopping is more fun. Which equation do we have here to help us find distance or time, I guess? Third one. Okay, so the third one is A equals VF minus VI over time. Now, is that going to help us with distance? No, but will it eventually help us with distance? Yes. You could also use this equation number 5. Will get you there as well, right? Because the VF, this thing goes away, and then you have an acceleration distance and initial velocity. But let's solve this one. This looks pretty fun. We're trying to solve for time. So we just switch these. T equals VF minus VI over acceleration. VF is 0 minus 12 over negative 9.8 time equals 1.22. Now, does this help us with the question? Is that an answer? Does that help us with distance? Kind of. We go shopping again. Now we've got some more money. Found some change in the couch. Now we can do the first. So VAV, distance, and time. VAV equals D over time. Solve this for distance. VAV times delta T, distance equals 6 times 1.22. What do we get here? 7.32. So now, again, our first blitz was what? What the question asked us. Was the maximum height above the ground the projectile, or in this case the football, reached? 7.32 meters. What about the second question? What's the second question ask us? Now that we've got a bunch of information figured out. The time of travel before the football hits the ground. How can what we just found help us?
Multiply time by 2.
Ooh, y by 2.
Because it was 1/2 and not a half.
Yeah, so think about what we just solved for here. Right? What did we just solve for? We solved for the height to get to this point, right? We kind of figured out this whole side of this scenario. And we solved for time because that variable was there. We didn't necessarily need it as the answer, but we needed it to get to the answer. Right? How can we use that number that we found for time to inform the rest of the question? Right? However long it took to get to that spot at the top, that's going to be the same as what? Time it takes to complete the other half. So to figure out the total time for this projectile is just what? the time for this to peak times 2. Right? And again, this isn't necessarily an instruction. This was in the APP. This was part of the physics to go last night. For those of you that completed those or worked through those, this probably looks familiar. For the rest of us, maybe this is something intuitive that we need to think about, which is fine. So what's our total time for the projectile? Let's go back. Total time to peak times 2. Total time. So 2 point, what will we have, 1.22? So 2.44? What is our third blip? Total distance. Total distance is? So now what are we talking about? What dimension are we talking about? Horizontal. We want horizontal distance. So now we're back to the drawing board. We're going to need total time. I'm just going to keep that up here. Now we're in horizontal. Let's start filling in some blanks here. What's our initial velocity in the horizontal direction? 16.0 meters per second. How did we find that? The question didn't give us that. There's no 16 in the question. How did I find this number? Where did the 16 come from? Yeah, way back when we did Sokotoa at the very beginning, and we broke this down into horizontal and vertical velocity. What's our final velocity? 16. Did this number change? No. Right? This is horizontal motion, so it's still 16. What's our acceleration? Horizontal acceleration. 0, doesn't change. What's our distance? That's what we don't know. That's what we're solving for, right? What's our time in the horizontal direction?
4.
That's what we just solved for a second ago, right? Still hiding up here. And lastly, what's our average velocity? 16, it's the same. Now what do? We go shopping. What formula is going to help us? Top one. OG formula. VAV equals delta D over delta T. We're solving for distance. Distance equals VAV times T. Distance equals our velocity is 16.0 times 2.44. Distance equals 39 point. Give me 3 stick figs, bro. Okay, 39.0 meters is our third blip. Leave the fourth blip to you.